Excellent. Welcome everyone. Good afternoon. So today is the last day that you will see me teaching. All the others should be both James and Daniel. But let's make it count, okay? So as usual, let's go some reminders and then we'll move on to the meat of today's lecture. I will also try, if I have time at the end, to do the purification and distillation that we did not have time to do last time. It fits well in this lecture, so you are not losing out with the reshuffling and everything. But first and foremost, let's start with the noise. So we'll start with the reminder more specifically. And let's start with the reminders on the reduced density matrix. So if you have, let's say, 2 qubit systems, but in truth it can be any system that has at least 2 partitions, then at least for 2 qubit system you can write the wave function of the system like this. Okay, it's a very generic writing. You can write the reduced density matrix associated to this pure state by writing it this way. And if you write it in matrix form in the local basis, that is to say in the basis of zeros and ones, then this is the row that you will get. Okay? I wrote it this time because like this, because this way you know where the C, the A, and the stars goes in. If A, B, C, D are complex numbers or real numbers, you can put them in any order. But if instead this is a more modelization of a more complicated system, and the A's and B's are like matrices, for example, then there is then the order starts to matter. The order starts to matter. And the order here is the correct one. Okay. Now you can wonder, or you can ask yourself the question, what is accessible if now I only have available the qubit 1? So the state of my two qubits are in is this one, but for whatever reason, I only ever have access to a single qubit. What are the kind of question I can ask to these qubits? Well, question in quantum physics is more generally asked using an observable. Okay, so what are the kind of observable that we can query when we only have access to a single qubit? Well, they are observable like this O1 over there, that are written as O1 that is applied, that is acting only on the first Hilbert space in tensorial product with the identity. Why tensorial product with the identity? Because we don't have access to the second qubit. To get the expectation value of this observable, you take the trace of rho times the observable. Because the observable O1 here only acts on the first Hilbert space, you can decompose this trace into first the trace on the second Hilbert space and only then the trace on the first Hilbert space. So you can write it this way. And when you trace over the second Hilbert space, then what you will be tracing upon, because of the identity here, is only the trace over the second Hilbert space of rho. And this we saw is something called the reduced density matrix rho 1. Therefore, to get the expectation value of O1, an observable only acting on the first Hilbert space, I only ever need rho 1, the reduced density matrix, on the first Hilbert space. Okay? Rho 1 is enough for any observable that acts only on the first Hilbert space. If we want more details, more, let's say, computational details onto how to do this partial trace, then let's say, for example, that I want to do the partial trace over the second Hilbert space of some random matrix A, or some random observable A, or some random density matrix A. Then the partial trace will look like this, where here I sum over the expectation value of a set of basis states of the second Hilbert space, psi I, psi 2I. Okay? Psi 2I is a basis of H2, where the full Hilbert space of the 2 qubit system is composed by H1 in tensorial product with H2. Okay? Let me check that this guy is still recording. I think so. Then using let's say that we want now to perform the partial trace over the second Hilbert space over rho that I've written over there. So to remember how to do the computation, I will wait for your input over there. But so the trace is a sum over the expectation value of rho over a basis of the Hilbert space of the second qubit, that is to say 0, 2, 0, 2 and 1, 2, 1, 2. Okay? When I do 0, 2, 0, 2 on rho, what do I get? If I look at either this expression or this expression, whatever you prefer. Or even the third one. Yes?
A of t.
Okay, let's forget about the t just to make it more, to make it a bit easier. So you said just A? Not quite. Because remember, this is psi, but here what I'm taking is rho. So if I were to look at indeed the very first term, I would have, for example, 0, 2, A, 0, 0, but 0, 0, A star, 0, 2, right? Meaning that here I have some A and some A star that are multiplied, and so this term here will give me modulus of A square times 0, 0, where here of course it's 0, 1, 0, 1. Okay? So this is the first term. I sum you over 0, just so that I don't have too much term in the blackboard. Let me just rewrite modulus of A square here, 0, 1, 0, 1. Okay? Then second term is, for example, the one that is over there. It would be A 0, 0, 1, so 0, 1, B star. Okay? But it means that I have a 0 on the left, a 1 on the right. Whereas here I have only a 0 on the left and a 0 on the right. So on the right I will have a 1 in a scalar product with a 0. And this is equal to the scalar 0. Therefore this term doesn't matter. This term over there. This term over there, will it matter? No. Too bad, it does. Because you will have, let me write it down. So you have some AC square times 0, 2, 0, 0, 1, 0, 0, 2. Again, 1, 2, 1, 2. Okay? 0, 2, 0, 2 is 1. 0, 2, 0, 2 is 1. And therefore, this term will just be AC star 0, 1, 1. Okay? So this term does matter. Again, let me erase this so that I have a bit of space on my blackboard. Okay? Does this term over there matter? The AD star? Alright, let's do the computation together. So what is the term that will multiply my AD star?
0, 2, 0, 0, plus 1, 1. And then 0, 2 again.
That's right. 0, 2, 0, 2 is
0.
no. 0, 2, 0, 2 is a 1. When you have 0, 2 or anything, 0, this is equal to 1. 1, 1 is equal to 1. 0, 1 is equal to 0. And 1, 0 is equal to 0. This is what an orthonormal basis means. This you saw many times, right? So this is exactly the kind of formula that I'm using here. So here I have 0, 2, 0, 2. So 0, 0 is 1. So this term will be just 0, 1 over there. So this 0 here that keeps. Apparently there is some maybe uncertainty into what this stuff means. So let me again decompose that stuff. So when I write 0, 2, 0, 0, 1, 1, 1, 0, 2, for example, what it actually means, or what I actually mean is 1, 1, so the identity in tensorial product with just this 0, 2, applied on the state here, 0, 1 in tensorial product with 0, 2. That is in outer product with 1, 1 in tensorial product with 1, 2. That is in a scalar product or partial scalar product, or that probably has a more complicated mathematical name, with the identity applied on 1 in tensorial product with 0, 2. Okay? This is the writing, the shorthand writing. This is the shorthand writing of that stuff. Okay? When you have things written this way, you can put them all together. That is to say, you can write that it's 1, 1 applied on 0, 1, that is in outer product with 1, 1, that is applied, that is acted upon by 1, 1. And this is in tensorial product with 0, 2, applied on 0, 2. In this time, it's either the adjoint product, but this in that case coincide with just the normal scalar product with 1, 2, 0, 2. Okay? Then when we have that, we know that the identity doesn't do anything. Therefore, we have 0, 1 left in outer product with 1, 1. And this is in tensorial product with something that is by default. So here I should not even put this guy because this is closed by the 0, 0. So this is just a normal product. But this would be the part that is given by what's left of the second tensorial product. And the first scalar that we have here is 1, as I mentioned earlier, because of in virtue of the fact that we have an orthonormal basis. And similarly, this 1, 0 here is equal to 0 in virtue of us having an orthonormal basis. And so what we are left with in this case is 0, because 0 times whatever is equal to 0. Okay? So this is the full decomposition of the entire computation. There is really nothing difficult about that. It's just about setting the expression right. If you still have some doubts about that, there is only one thing to do, is to try again and again and again until you have it. Okay? It's really nothing complicated in and of itself, but it does require you to understand what are all the convention that goes behind these notations. Okay? And these notations are relatively popular because they work real well and they are very intuitive. Yes?
Where do we take the outer product between 0, 1 and 1, 1 and not, for example, 0, 2 and 1, 1?
Where? Here?
In the second to the first.
From here to there? Because here I regrouped everything with terms that belong to their own Hilbert space. Mm-hmm. Okay? So it's like saying, I don't know, if I have, so I'm not sure this example will help if you're not familiar with the vector notation, but let's say I have something like this, AB, that is in outer product with, I don't know, 1, 0 and CD, for example. Then what you're actually doing is that you are doing the outer product of this guy in this guy, that will be in tensorial product with the outer product of this guy and that guy. And it's not that you do the outer product between this guy and that guy, because here the convention is, this is in space 1, this is in space 2, this is in space 1, this is in space 2. And the outer product only combines the same space. So there is no mix between 1 and 2 and 2 and 1. We can go into the mathematical definition of why this is like this, but it's just a definition as which is a little bit more than just a convention of notation. This is how it works. There is no demonstration for that. This is what the mathematical notation means. Okay, this is how we are supposed to do the thing. To try to put a bit of physical insight as to why, well, it means that if you had an operator like 0, 1, 1, 2, for example, so you should not write that, but let's have some philosophical thought about stuff like this, then it would mean that here, the Dutch operator here will destroy the state 1 on qubit 2, transforming it into the state 0 in qubit 1. But this is weird because it destroyed the state 1 on qubit 2, but so what happens to qubit 2 afterwards? It's not like it disappeared from existence. The physical qubit is still there. But this operator here just remove its state and doesn't replace it with anything. Similarly, what it does is that maybe the qubit 1 was like having a nice time on its own, and suddenly, without like any kind of warning or interaction, it turns into 0, 1. It makes little sense. What makes sense is transforming the state 1 of qubit 2 into some other state for qubit 2, and transforming a qubit, the state of qubit 1 that was whatever into the state 0 for qubit 1. Okay? So this is why something like this doesn't make any sense. Is it clearer now? If it's not, and even if it is, I strongly encourage you to just redo this at home. And I'm pretty sure there will be some exercises that relies on that. If not already, then in the future. Okay, so we had this guy. We saw that we had a 0, 0 here and a 1, 0 over there. 1, 0 leads to a 0, therefore this term here is not important. All right? If we go with the BA star over there, well, either you can do the computation once again, and you will see once again that you have a 0, 1, and therefore this is equal to 0. Or you could also remember that this was a 0, and that everything is very much symmetric in this business, and therefore, if this was 0, there is a very, very good chance that this guy is also 0. And sure enough, it's the case. Similarly, this guy over there is, we have to account for it. And this guy, however, will give us a CA star times 1, 1, 0, 1. Okay? This guy over there will be a 0, same as here. Then we have some B square over here. So B square, so modulus of B square would be some 0, 1, 0, 1. So the addition with this 0, 0 doesn't give anything. But this part of the sum, the one with the 1 on the left and the 1 on the right, now this guy contributes and leaves just 0, 1, 0, 1 after doing the computation. Meaning that this guy is added over there. So this is about this term. This term now, does it contribute? Does it not contribute?
Which one?
So it's this CB star. Or I guess we can do the BC star. It's the same because it's symmetric. But so if we do the BC star, we have some 0, 1, 1, 0. Meaning that looking at just the second qubit, we have some 1 on the left and 0 on the right. 0 on the left and 0 on the right is incompatible. 1 on the left, 1 on the right is incompatible. Therefore, this guy is equal to 0. Yes? No, it was not a question. Okay. So this guy does not contribute, also not this guy. This BD square now gets us some 0, 1, 1, 1. Ah, now this is good, because it means we have a 1 on the left, a 1 on the right. This is possible according to this other term over there. What is left, or what remains after doing the operation is a 0 on the left, a 1 on the right. And this is what we have over there. And therefore this will be the term B D star. Okay? Similarly, this guy will be non-zero by symmetry, but because we have to take the transconjugate, now this guy will be over the second term over there. Let's see what else is there. There is the modulus of c square. The modulus of c square will contribute, as all the diagonal terms do. And what is left, well, by looking at just the modulus of c square, is some 1 on the left and some 1 on the right. So we have some 1, 1, 1, 1. If I look at CD star, this will be 0. Same for DC star. And what is left is the modulus of d square that will contribute, because it's a diagonal term, and it will contribute to 1, 1 in particular. Okay? Redo this computation at home. Very important. If I were to rewrite this expression in terms of a matrix, this is what I'll get. We saw that the diagonal terms are the probabilities, that is to say the probability of finding a 0 and the probability of finding a 1 respectively for the first qubit, whereas the off-diagonal term were called the coherence. All right? Then we saw that both the density matrix and the reduced density matrix verifies a whole lot of properties. One of these properties is the conservation of probabilities, that is to say that the trace of rho or any reduced density matrix is equal to 1. Okay. Furthermore, there was this notion of purity. So if we were to take the trace of rho square or rho 1 square, then we can show that it's always inferior or equal to 1, and it will be equal to 1 if and only if it's a pure state. How to demonstrate this? Well, here is the proof. So let's say that rho 1 looks like this. Here A can be either a matrix if you want. In that case, it's not just a single qubit that I'm looking at, but more than that. Or if I am looking at a single qubit, then these are just numbers. Okay? If I were to look at the trace of rho 1 square, I will have, well, first I would need to multiply rho 1 with rho 1, and then takes the sum of the diagonal terms. This is what I'll get. I'll get, of course, a1 square, or I guess modulus of a1 square, I should write. But the diagonal term is always real, so it's a bit redundant to put this. Here, I have not written it, but no, it's fine. It's fine as it is. This would be the trace of rho 1 square, and these terms, these cross terms over there that are multiplying the coherence with themselves, are some terms that are called the interference terms, and this is in parallel with what happens in optics. And sure enough, if you were to write the quantum state of photons or your light in terms of the density matrix, and then look at the intensity of your light at a certain point in space, then you will observe that there will be these interference terms when there is interferences. Okay, so it's just not a parallel, it also works on one-to-one with the actual problem of quantum light. In any case, if now the coherence are equal to 0, that is to say A12 and A21 are equal to 0, then the trace of a rho 1 square is reduced to just these diagonal terms, square. And as you know, if these diagonal terms are real and positive and both strictly inferior to 1, then the sum of their square will be always inferior or equal to just their sum. And their sum, by definition of the conservation of probability, is equal to 1. Therefore, we just showed that the trace of rho 1 here, square, was inferior or equal to 1. And when is it equal to 1? When is that stuff here equal to 1? Well, it is either when A11 is equal to 1 and A22 is equal to 0, or when A11 is equal to 0 and A22 is equal to 1. And when this happens, we have a biseparable state. If I'm looking at just a single qubit in the case of rho 1, then more than a separable state, psi is almost certainly a pure state. Okay? As long as whatever was on the second qubit was not a mixed state already. And so, in that case, psi can be written like this. What it means when psi is a biseparable state is that there exists no entanglement between the first partition and the second partition of the system. In the case of 2 qubits, between the first qubit and the second qubit of the system. Okay? If I start with a non-separable state, this time, and I do a partial trace over one of the partition, then I will always be left with a mixed state. This is the kind of question that we studied in length last time. Finally, we can move on to this notion of decoherence. So if I start with rho 1 of my system that is connected with the environment, even if I would like that it wasn't, but it is. So that it wouldn't, yeah. Then as time goes to infinity, in virtue of this connection that it has with the environment, in virtue of this interaction that it continuously has with the environment, then rho 1 will converge towards this rho thermal state that is typically written like this, where here you have some function that depends on the temperature, T, as well as the energy of the state 0 and the energy of the state 1, respectively. Okay? What this function f is some statistical distribution that is either Bose-Einstein, Fermi-Dirac, or Boltzmann, depending on the kind of problem that you're looking at. It can be more complicated in more complicated problem, but it's not very important for us. Okay? So in that case, two things can happen. Let's see if it's still recording. I hope it is. I think it is. Two things can happen, or two things have happened during this process. The first thing that one can see is that the coherence term here have converged towards 0. Because the coherence disappeared, we call this phenomenon decoherence. Okay? Not only that, but also the probabilities of finding a 0 and finding 1, also those have changed. And they went to this function of f depending on E0 and E1 respectively. This distribution here gives us information about the temperature. It gives us information about the energy of the state 0 and the state 1. It gives us some information about the statistics of the kind of system that we are looking at. But it certainly does not give us any kind of information about the initial state of the qubit. That is to say, about what rho 1 was. Okay? So this is why such a state has lost the information that we had encoded into rho 1. And what is left just tells us some things about the environment and not about the system itself. Okay? So whatever information was there is lost through the decoherence process. And the decoherence process is the most common process of noise in a quantum computer or in any quantum system. Okay? So, now that this is seen, we can say that typically we have P0 t, so as a function of time, will be something that is proportional to P0 of 0, so whatever the probability was when the processes start, times some exponential decay, plus the function that is given by the distribution times whatever is needed to compensate the decay of the first. So through decoherence processes, the information decays exponentially with this factor that depends on T1, whereas the noisy leftover increase conversely. Okay? If we look at the coherence, how they evolve with time, then typically this will be proportional to whatever the coherence was at t equals 0 times some other exponential coefficient that is this time controlled by the parameter t2. Now you can ask, or you can wonder, how does this happen? How does this happen? And this is exactly what we'll mention today. Specifically, there will be two ways. One way is an average over classical noise. So let's say that what I'm doing is that I'm doing a series of gates but on the qubit, but every gate is a bit faulty, so sometimes I'm making my gate last a bit too long, sometimes a bit too short, and so on and so forth. And so as all of these error averages, then my result will get worse and worse, and what I'm left with is some matter of mixed data in the end. So this is one way that can lead to a diagonal state. Okay? But there is also, and perhaps most importantly, the average over this time the quantum noise, and specifically the average over the interaction of the system with the environment. And a typical way to represent this stuff, this process, is through a Lindblad equation. So I mentioned the term here if you ever go there, but we will not go there together yet. Just wait an hour and a half. So it follows that the coherence here is not only controlled by the time that it takes for the system to relax to its so-called rest state. Okay, the rest state is the state of the system at the end of a relaxation due to its interaction with the environment, but also due to terms that are specific to the decoherence process, so through the dephasing of the qubits. And because it's sometimes useful to do that when we talk about it, then we say that T2, this time T2 here, is both a function that is a function of the relaxation process T1 and of the dephasing process T phi. Okay? The dephasing process being whatever process that acts on this specific stuff over there. Okay, this is the phase. I think we already mentioned that before, but just in case. This is the phase, and these are the amplitudes. All right. These are reminders, let's say rich reminders. And finally, we can start the content of today. Before I start with the content of today, are there some questions about these things already? Yes?
I was just wondering about the phase.
Yes.
This is not the global phase, right?
No.
Yeah.
A global phase would be some exponential I var phi that is in factor of the entire state. And this global phase, indeed, we don't care. Yes?
What's the first letter and what's it stand for?
Here?
Yeah.
This is a P, and this is also P. This is a curly P, and this is a cursive P. It's the same, it should be the same length. Okay? And this would be the probability to find 0 if I were to measure my first qubit. Here the probability as a function of time. And P0 of 0 means when the time is equal to 0. This is A0. Other questions? Great, then let's move on. So, let's discuss first some phenomenological model of the noise through T1 and T2 processes. So here I will show you a bit of more complicated math than usual. This math is not very important, so you don't need to necessarily understand how to redo it yourself, but it's good to have a look at it to see more or less how things work. Okay? So, but before going to this math, let me discuss a bit about the model. So we imagine two kinds of phenomenon. For example, we can imagine that the qubit that we have is some spin qubit that is interacting with both the magnetic field that exists due to the apparatus it is in, and that also interacts with the light field, so the electromagnetic field. Okay? So two things can happen. First, we can have spontaneous emission, or spontaneous relaxation is the same stuff. That is to say that the spin up can turn into a spin down. So we say that there exists a process, and we don't really care what it is, that turns the plus state into the minus state, or the up state into the down state, okay, through a rate that is given by gamma. Here, this is an uppercase gamma. And as we do so, the light field, the electromagnetic field around, gain a photon. So the state of the electromagnetic field without photon, written with a 0, turns into the state chi. I could have used 1, but to make sure that you know that this is a photon and not a qubit, I put chi. It's just a name, we can do that. All right? So this is one process. In this case, I only have spontaneous emission, so I don't consider reabsorption. In reality, there is reabsorption, but in this model, I forget about it. Okay? Another process, though, that I do not forget about is the dephasing due to random changes in the frequency of the system. That is to say, that imagine that the experimentalist that has this qubit has a cat, and the cat is now playing with the button changing the intensity of the magnetic field. The magnetic field, make the spin precess, okay? Meaning that depending on the intensity of the magnetic field, the precession pulsation or precession frequency will change, and will change by an amount that is only decided by the cat, which is, for as far as humanity has understood, completely random. Okay? So we say that this dephasing happens according to a frequency omega t that is equal to omega 0 plus some delta omega I when t is between the time j delta t and j plus 1 delta t. Okay? There is a lot of cats in quantum physics. They are both useful and problematic. And of course, the value of delta omega I is chosen by the cat. That is to say that it is random. Okay? This is my phenomenological model. Now, because it's a useful computation, I will perform it now and use it later. But this way it makes the reasoning a bit more consistent. So, if I call phi of t the integral between 0 and t of omega t dt, that is to say the total dephasing that is happening between the time 0 and the time t, okay? Then this is by hypothesis. So by hypothesis we have t is equal to n times delta t. Then if you want to compute the average over the cats of phi of t, so the average over the experiment, that is to say if now instead of having one qubit like this, I have 10,000 of them, each of them has a cat playing with the intensity of the magnetic field. And then I want to understand what is the average value over the cats, that is to say over the experiment of this operator here. And I want to know that because later I will need it. So just trust me that this is an interesting stuff to compute. Then by definition of where it comes from, this average value is equal to exponential I omega 0 t, the constant part, times the average over the cats of exponential I delta omega 1 delta t plus I delta omega 2 delta t, and so on and so forth until I delta omega n delta t. Right? The cat is completely spontaneous. That is to say that he will push the button at a certain time completely independently on how he pushed it before. That is to say that the value of delta omega 2 here is completely independent from the value of delta omega 1 or the value of delta omega n. That is to say that when we do the average, we might as well average over each of these time intervals separately. In other words, this is equal to exponential I omega 0 t, exponential I delta omega 1 delta t, average times the average of exponential I delta omega 2 delta t, and so on and so forth until exponential I delta omega n delta t. And because it's not like the cats change their mind as time goes on, the average over delta 1 is the same as the average over the delta omega 2, is the same as the average over the delta omega n. In other words, this is just equal to exponential I omega 0 t, exponential I delta omega delta t to the power n. Okay? If you don't exactly follow, you can just trust me, it doesn't really matter if you don't get it fully. But we can discuss about it at the end if you're still interested. So we have this result. Then finally I make one last assumption about my cat, which is actually not such a bad assumption, is to say that my cat now choose how it will push the button according to a Gaussian probability distribution. Okay? If the cat really doesn't know what he's doing, actually a Gaussian distribution is not that bad of a guess. And if you were to average over this function here of a Gaussian distribution, then what you are actually doing is the Fourier transform of this Gaussian distribution. And as at least the student in physics among you can say, the Fourier transform of a Gaussian is a Gaussian. Exactly. Yes. And as a consequence, what is left over there is, well, just another Gaussian. So we have this times exponential minus delta omega delta t square divided by 2 to the power n. So this is if delta omega follows a Gaussian. Okay. This is the result that I wanted, so I'll just keep it in mind for now. I promise it's useful. Erase this. Now that we have this computation, I can go back to my model, and I can go back in particular to what I expect my wave function to look like. This. Because of the first term in, so let's say that we start with some random superposition. So we want to know what psi of t may very well look like. Well, we know that at the beginning it looked like this, plus some minus 0. So here there was some alpha 0, and here there was some beta 0. Okay? At least when t equal to 0, this is what it was. This is what it looked like. All right? And then we have these two processes that are happening. Specifically, we have the spontaneous emission. The spontaneous emission will make it so that we have this rate. Therefore, here we'll have some exponential minus I gamma t over 2 that are reducing the state. It is not doing anything on this state over there because there is no relaxation to get when starting with minus. But of course, there is some increase with the rate square root of 1 minus exponential minus gamma t. That is turning this plus 0 state into the state minus chi. Okay? Why is it a weird square root of 1 minus gamma? Well, it's to make sure that everything stays well normalized. Okay? So if you put this guy over there, you have to put this guy like this over there. Why did I put a 2 here? Well, I could not have, but then here I would have had a 2. Doesn't really matter. Here it's a phenomenological model, so we don't really care about the factor 2. All right, so this is when I just account for the first process, but there is also this process of dephasing. So this process of dephasing will make the spin process differently if it is in the plus state compared to the minus state. Okay, so if it is in the plus state, there will be an extra term that is in, I'll just put it there, it doesn't matter where it is, in exponential minus I phi over t divided by 2. Here there will be the minus state, so that it is an exponential I phi over t divided by 2, and here it's also a minus state, so there is again this exponential I phi over t divided by 2. Again, I could have, if I wanted to, not put a 2 over there, and there, and there. It doesn't matter, it's just a factor 2. Or what I could have done is here not put a 2, and here not put the dephasing, because then I would just be in the rotating basis of the minus state, for example. All of this will give the exact same result, so it doesn't really matter. This is an arbitrary choice. I made it. What is important is that the sign between what is in front of the plus and what is in front of the minus is different. This is what really matters. Okay? All right? This is something that at least phenomenologically describes well the system that I have came up with my model over there. And so now we are just trying to, well, extract T1 and T2. Specifically, what we want to compute is rho plus plus as a function of t and rho plus minus as a function of t, where these rho plus plus and rho plus minus are one of the diagonal term in the reduced density matrix of the system that only involve the spin, and rho plus minus is one of the two coherents of the system that only includes the spin. Therefore, what I will have to do is first write the density matrix of the full state over there, then do the partial trace over the electromagnetic field, which is nothing much than another qubit in disguise, huh? So it's very relevant for you. And then after I'm done with that, I have to compute this average over the cats. Okay? So let's do that in order. Okay. So I don't know how much you want me to go into details, because it's nothing else than just redoing what we did at the beginning. So maybe you can just recognize that here you have the exact same expression of the psi that I gave you during the reminder. You know, the one that led to a very big matrix, a 4x4 matrix, where this for example is A, this would be C, and this would be D. Okay? And B, as it turns out, is equal to 0 in this specific expression. Okay? It makes things a bit easier. And then, if you were to compute rho spin, okay, that is to say the rho 1 that we had earlier, we had the formula, maybe it's still over there actually. No, it's not. We had the formula that this was modulus of S square plus modulus of B square over there. Here it was A C star plus B D star or something like this, and so on and so forth. So you just replace with all of these values over there. Note that rho spin, according to this convention, is rho plus plus, rho minus plus, rho plus minus, and rho minus minus. Okay? And if you were to do that, then you will see that rho plus plus as a function of t is nothing else but modulus of alpha is equal to 0 square times exponential minus gamma t, no I, minus gamma t. Okay? And therefore, if I now were to do an average over the cats, well, it won't change anything because there is no cat involved in this formula. If now I look at rho minus minus, just for the sake of things, then you will see that this will be equal to modulus of alpha 0 square times 1 minus exponential minus gamma t plus modulus of beta square. Sure enough, when t is equal to 0, this is just modulus of beta square, as we expect. But there is some extra probability that is coming from the modulus of alpha square due to the relaxation process. Because we need that stuff and that stuff to always be equal to 1, everything that is lost over there is gained over here. And of course we have modulus of alpha 0 square plus modulus of alpha beta 0 square is equal to 1. So everything checks out. Again, if we do the average over the cats, nothing changes because there is no cats involved in this formula. Finally, and most importantly, if we were to look at just applying the formula and looking at rho plus minus, then what we will see is modulus of alpha 0 square, exponential minus I phi of t minus gamma over 2t times square root of 1 minus exponential minus gamma t plus alpha 0 beta 0 star exponential minus I phi of t minus gamma over 2t. Okay? More or less, where does it come from? This square root of 1 minus gamma t comes from these terms over there, but because it's a coherence, it's in a cross term with another of the terms that gives us the gamma over 2t over there, plus of course the phi of t that is coming from both this guy and that guy, so that's why they sum up. Sorry, from this guy and that guy, that's why they sum up, because you have to take the complex conjugate of one of the two. And this is the other terms, and this is what you have left. Okay. If we now were to do the average over the cats, well, where do the cats come along? It comes along in the expression of phi. Okay, so I cannot just neglect it or discard it like earlier. I have to do this computation. So what I'm left with, if I were to factorize with this exponential minus I phi of t, would be modulus of alpha 0 square exponential minus gamma over 2t square root of 1 minus exponential minus gamma t plus alpha 0 beta 0 star exponential minus gamma over 2t times this average over there. How do I compute this average? Well, this is exactly what we did earlier, and in particular we saw that this was nothing else but exponential minus n times delta omega delta t square divided by 2, okay, times exponential I omega 0 t. All right? Minus, because there is a minus over there. N times delta t is equal to t, and therefore this expression is just equal to maybe while I erase the blackboard, you can think of what the expression will be at the end. So I have this rho plus minus t that is equal to so maybe I take the first term, the one that is a way that can be extracted from the parentheses by factorizing as much stuff as possible. I have some exponential minus gamma over 2t exponential minus n delta omega square delta t, and this is not an n, this is a t divided by 2, exponential minus I omega 0 t times modulus of alpha 0 square root of 1 minus exponential minus gamma over t plus alpha 0 beta 0 star. And this is equal to this stuff over there. So if I take the tin factor, exponential minus I omega 0 minus gamma over 2 minus t delta omega square delta t divided by 2 times something that is a constant at long time, but also its initial value when the time was equal to 0. At long time, t goes towards infinity, so exponential minus gamma t goes towards 0. It means that this rho plus minus infinity is just the modulus of alpha 0 square plus alpha 0 beta 0 star. It's a constant, we don't really care, because we only care about what happens at long time. So we have a certain constant over there, and of course when t was equal to 0, then this was just equal to alpha 0 beta 0 square, which is the coherence that we would expect from the initial state. So what really is important in this expression is this prefactor over there that happens to be an expression that is indeed an exponential in time, where this prefactor here is exactly what will give us the value of T2. So to summarize, we have rho plus plus of T that is equal to, so what we expected was something that is proportional to some exponential minus T divided by T1. By just reading the expression over there, we identify T1 with what? With 1 over gamma. So the inverse of the rate of decay, and that makes sense. The relaxation happens with a decay rate given by gamma. And so the invert of gamma is the lifetime of the excited state. And similarly, if now we look at rho plus minus of t, then we expect this guy to be proportional to some exponential minus t divided by t2. And just by reading this expression over there and noticing that this exponential I omega 0, we don't really care because it's just a running phase, then we deduce that 1 over T2 is equal to, so minus gamma over 2, but we can replace this expression of gamma over there, so we can say that it's just minus 1 over 2T1. Sorry, plus, of course, because the minus is in factor, plus this stuff over there that I will just call 1 over T5, the pure dephasing term. Why pure dephasing? Because in my model, I call the process that is responsible for this term the dephasing part. Okay? And so this, as a consequence, is just equal to 1 over T5. It follows that we have that T2 is a function of the relaxation process and the dephasing process. In other words, the decoherence term is a combination of the relaxation and the dephasing, whereas the relaxation term is a consequence of the relaxation. A bit tautological, but it's good to make sure that everything is consistent. So we have this. This phenomenological equation is actually quite generic. It is still recording, good. It is quite generic, and especially it shows that T2 is inferior or equal to T1 in the extreme majority of noise processes that you can imagine, like 99.99%, this relation is always verified. Okay? So you might as well say that it's always the case. And yet we managed to derive it with a super, super simple model. You cannot get more simple than that, actually. And so what is interesting from this formula is that as a consequence, whatever is happening in the coherence will always have a lifetime that is smaller or about equal to the relaxation process. It also means that if you want to, for example, encode information or have the crux of your algorithm that is happening in the phase of your system, then actually you are putting all of your effort in the worst possible place. Because whatever kind of noise end up happening, this is where it will happen the fastest. This dephasing is what will happen before anything else, especially before the relaxation. So if you have the choice, rely more on encoding your information into the amplitude, that is to say, into the fact that you have a 0 or a 1 or a certain superposition between the two, but do not encode your information or the crux of the algorithm inside the phase. So this exponential minus I phi that was written earlier. Okay, why? Because this is the first information that disappears. Always. Okay? So this is the conclusion of this stuff. And it also tells you what are the effects of the so-called T1 and T2 process. Here, I've put that it's only phenomenological. I just said, okay, let it be that it's like this. But you're probably saying, wait, okay, that's a good way maybe to get into it. But if I'm now looking at another hardware, this model does not hold anymore. Strictly speaking, it's true. Depending on the hardware, depending also in the time of the day of the hardware, or some specific combination that you end up doing, the model will be completely different. Every time something else. Okay? So while it is possible to relatively well account for a good chunk of this noise, it remains that every time it is different. But so it means that if you are now a hardware provider and you want to sell your stuff to other people, if you really want to be exact, they basically have to learn everything that you know before understanding you. That doesn't do well. And if you try to market something and you have to first convince someone to do a PhD in a specific domain to understand what you're about to say, you're not going to sell anything. Okay? And so what instead is used are heuristic, some very coarse-grained modelization of the system, some very coarse-grained modelization of where the noise is coming from, and value that are quantifying this noise. And the first one that we see today is this T1 and T2 value. So when you look at the calibration data of a hardware provider, they will very often give you a value for T1 and a value for T2. Clearly, they may not care about how their qubit is interacting with the electromagnetic field, but it doesn't matter. Those are details. What matters is that what T1 and T2 means, that is to say, the relaxation process and the decoherence process. Okay? So first kind of noise that we see today are this T1 and T2 process. And this is exactly now that we'll do a bit more into details. So accounting for the calibration data. Calibration data, which is something that you almost certainly will have to do if you ever end up doing some sort of quantum computing software. Okay? Unless someone is doing it for you, but then it's always the same. Huh? If someone else is doing stuff for you, then what are you doing? So if, let's say, you exclusively have some T1 and T2, this T1 and T2 will vary depending on one qubit or the other. So ideally you want to account for this T1 and T2 for each and every single qubit. Then you can actually use the same modelization as before to see what will be the effect of T1 and T2 on your system. That is to say, you can use the same kind of formula that I've used over there. This are your expectation. This is what T1 and T2 means, even if they are just a very simplificating modelization of your problem. Sometimes, and I put it there, you are given a T2 and a T2 echo. Just take the T2. The T2 echo allows you to get a refinement into your modelization, but we'll not do it there. So I'll just mention it to you now. So in Qiskit, how do you account for this kind of modelization? If you want to do a noise model, for example, then you can build your error gate by making some sort of list with something that is called the thermal relaxation gate. Okay, that will be a function that is built in Qiskit of your T1 and T2, that are the T1 and the T2 for a given qubit, and of course the gate time. That is to say that while the gate is being performed, the qubit on which the gate is performed will relax according to the time T1 and will dephase or decohere, according to the time T2. How much time does it take? Well, it takes the time it takes for the gate to be performed. That's why when you are looking at a T1 and a T2, you always have to compare them with respect to the various gate time of your system. Because if you have very big T1 and T2, then it means that you have a very long relaxation, that the relaxation takes a long time, and that the dephasing also takes a long time. But if the gate time also takes a long time, that is to say, if to do a single gate, it also takes you a while, then it doesn't matter that the first two are long. What matters is that you are able to do plenty of gates before T1 and T2 kicks in. But whatever you do, they will always kick in, even if it's just a little. Okay, so how to account for that? Well, you account it for that. And of course you do something like for T1, T2 in like some zip T1s and the T2s or something like that. If the T1s and the T2 are the list with all the T1 and the T2. All right, and then once you have something like that, then you can write some sort of noise model by being, so first you have to use the noise model function in Qiskit. If you use penny lane, if you use circ, if you use Q sharp, they all have their own syntax, of course. But so you do something like this for J in range number of qubits, whatever you call that. Then you look at some noise thermal is times no, I should have written noise model, I think. No, it's thermal time add quantum error. So this is again a Qiskit function of the error gate list that you have generated earlier with, here you put whatever gate is having this noise applied on J. So gate here is to be replaced by X, or I don't know Rx theta, or whatever they are called in Qiskit, okay? This is the correct syntax. And then to actualize everything with your model, then you do sim thermal. So the simulator that will simulate your noise will be something like RR simulator. If you use IR, with this argument that is the noise model. Whoops. Noise model equal the stuff that you just created. Noise thermal. Okay, and this is noise thermal. Of course, this is what I should have changed. Okay. And then later you use this sim model as your simulator for your experiments. So how to implement all of what we saw today in the various experiments that you will do? Well, this is how. Okay. How now Qiskit implement in detail the T1 and T2 processes or any other processes, this we'll see a bit later. All right? Is the stuff still ongoing? I'm amazed that despite all of the chalk, the fingerprint reader is still working fine on Mac. That's remarkable. All right. Let's move on. So we already know a certain kind of errors that we saw together before even the T1 and T2 process, and those were the confusion matrix. So let's go to that really quick, and also let's look at the reset error as well. It gives me the opportunity to do a small correction of something that I said, I believe, 4 weeks ago. So I was confused with the confusion matrix. So confusion matrices, so for measurement and resets for one single qubit. So we had something like P0 observed, P1 observed is equal to some matrix that I have written P00, P01, P10, P11 times P0 ideal, P1 ideal. Okay? All right? The line of these guys, if you were to do the sum, is equal to 1. And what I said the other time and was wrong, and I apologize for this, is that I said, even if I was called out for this, is that I also said that the column, if you were to sum the column, it would be equal to 1. It happens sometimes, but in general, it's not true. Sorry about that. I was thinking of something completely different at the time. These guys, they do not sum to 1 in general. Sorry. Okay? This stuff here is the confusion matrix. Okay? We saw the other time that we can mitigate at least this kind of error by taking the invert of that guy, and therefore by just looking at the observed probabilities, we can deduce the ideal probabilities, just taking, well, the observed time the inverse of the confusion matrix. Okay, this is a simple way of doing error mitigation. If now I were to look at the reset of qubits, so how do I initialize my state in plenty of zeros, for example, then there is also some mistake that can happen. Sometimes I can reset my qubit into a 1 instead of a 0, and I would not know until it's too late. So how do I evaluate this reset? Well, the reset, they also have some manner of a confusion matrix, except that this time usually you only consider resets to 0, so you don't need as many values. You just need 2 values: the probability of having what you want and the probability of having something else. The order of magnitude of this probability is very much the same as this one. So a way to remember, or like a mnemotechnic way to remember that it is the case, is because if, for example, you have some psi, then a way to reset whatever state you have here is to measure it. Okay, and then with what you are measuring, you do a conditional X gate to get a 0. That is to say that if you measure a 0, you do nothing. You start again with a 0. If instead you are measuring a 1, then you apply an X gate, and therefore you'll have a 0 this way. Almost always the measurement errors are much bigger than any single qubit gate error, and therefore the error of the reset is of the order of magnitude of the error of the measurement. In truth, what is really done in a quantum computer is rarely something like this, because that means that you have something that is called a mid-circuit measurement. In truth, and these mid-circuit measurements they do not exist yet in any quantum computer that I know of. Okay? A lot of people are trying to make them possible, but you need an embarked processor on top of your quantum processing unit, which is a catastrophe because it generates a lot of heat. So, and also it takes some space, and here everything is on top of one another, so you don't have the space to put that. So it's a technological challenge to do that, but this is a good way to get the idea as to why it is problematic like this. Okay. In truth, what is done is that we let the system relax. We just wait for it to evolve according to the kind of equation that we have written earlier. We wait a decently long time, and because the temperature is extremely low, it's effectively 0, and therefore the state will always relax to its single pure relaxed state, that is, by convention, the state 0. Okay? All right. Yet, if you want to implement this guy on Qiskit, then there is such a thing as a readout error, that will take into account the confusion matrix C. So you have to give it the stuff, and there is also the reset error that you can account. And this time you only have to give a single probability P. All of these things are again qubit specific, and then once you are done with that, you use one of these functions that are, in this case, add measurement error and add reset error, with this stuff as an argument. Okay. So you can also put some measurement error and some reset error. One last thing that is often given to you in the calibration data, besides C1 and T2, and besides the confusion matrices and the reset error, are the gate fidelity, or gate fidelities. Fidelity. So, the fidelity of the gate in particular, is this stuff over there. Square root of rho, sigma, square root of rho, square. Where sigma would be the density matrix of the target state, and rho would be the density matrix of the observed state. Observed state. So this is, strictly speaking, or rather rigorously, what the formula is. We will simplify it later. But what I mean by the target state is that sigma target is equal to what the state was before you apply the gate, and let's say that it is perfect, because in the formula it's best that it is perfect, especially that it is a pure state. And because you apply the gate on density matrix, you have the, no, it was my, you have the unitary matrix that correspond to the gate. And in this case, because it's the target, it's the unitary matrix of the perfect gate on the left, and it's transconjugate on the right. Transconjugate for a unitary matrix is the same as the inverse. Huh? So I'll write it as the inverse over there. For the observed state now, well, it's the same stuff. You start with the same initial condition, that is to say, your sigma perfect. But now, instead of applying it the perfect gate, you apply it the flawed gate. So it's also some u flawed and some u flawed over there. Now, some of you might say, wait, Pierre, wait a minute. Since now the gate is flawed, there is no real reason that the operation here is unitary. I can have a more generic Lindbladian operation instead. Not exactly this u over there, but something more generic. Yes, that's true. But let's make things simple for now, and let's just say that the flawed operation are unitaries. Okay? For what we will discuss about today. But know that it's like this, and you can do the same computation like this. So, right? If now we want to compute the fidelity, so this fidelity here, as a consequence, is a function of the perfect state that we start with. And therefore, the fidelity here is dependent of sigma perfect. Okay? It does mean that, strictly speaking, I would need to get a fidelity for each and every single possible state that I can put in sigma perfect, which, as a small reminder, is an infinite amount of them. Of course, no one does that. And instead, what we do is that we integrate over all the possible states over there. And we only have the average fidelity over all the possible initial state. Yes, your question.
Won't it be flawed inverse as well, if you're taking the transconjugate?
Sorry?
On the right side.
Yes, absolutely. So, the fidelity, as a consequence, fidelity will be some average over the d sigma with some normalization of this formula over there. Okay, this is the only thing that makes a bit of sense to give. Okay, fidelity that is written f will be this integral over psi ini. So here I consider that my sigma perfect is this psi ini, okay, to simplify my life, times u perfect minus 1 u gate flawed psi ini modulus square times d psi ini times some other normalization constant that is due to the fact that now I'm just looking at the state as opposed to the d sigma. And this is the important part, because here it would also require doing an experiment over all the possible initial state, which is madness. This is often approximated as just being 1/2 of whatever you have when starting with your state 0 time u gate flood, okay, psi ini, which is 0, okay, modulus square plus the same modulus of 1 u gate flood psi, sorry, not psi ini, psi, whoops. This should be u perfect minus 1, u perfect minus 1, and this is psi observed, of course. Modulus square. Okay? So here there is a complicated integral that corresponds to making an experiment over all the possible states. This is madness. Instead, what we do is that we just prepare the initial state being 0 as the initial state as being 0, the initial state as being 1. Okay? Then we apply this u perfect minus 1 that we know, because we know what gate we want to apply. So we have the exact expression for u perfect, and we observe whatever we observe in both the 0 basis and the 1 basis. Those are the probabilities of measuring 0 and 1 up to this u operator when considering the observed the observed state. Okay. Therefore, this is measurable for now, and this is measurable and obtainable by doing just something between 10 and 100,000 shots. So it's within reason. Okay. And this is what approximates the fidelities. And so when hardware provider give you the fidelity of a certain gate, what they are actually doing is that they are computing this value here. Okay? And from that, and from what u perfect is, you can deduce a phenomenological expression for what u gate flood is. How to account for that? Well, there is again a Qiskit function for that. We'll just have one example of something that is called the idle gate, so for an idle qubit. So the idle gate is not exactly a gate, but it's just what happens if you just leave your qubit B, so this I is the identity, then this idle gate, to this idle gate you can associate a fidelity, and let's say that this fidelity is 0.95. The fidelity is always between 0 and 1 by construction. Then what it means is that you have 95% chance that indeed nothing is happening, but you have also 5% chance that actually there was a flip. Okay? So, of course, for something as simple as the idle gate, you expect a fidelity that is much closer to 1, say 99.99%, but these guys compound. It's not that you have one idle gate or one X gate or one C0 gate, it's that you have several of them in a circuit. Each of them will have a fidelity that is not rigorously equal to 1, and so all of these mistakes will compound, each going into a result that is more and more away from what you expect, so that the entire circuit at the end of it will have a fidelity that is much, 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 much lower than 99%. It can go as low, well, it depends on the depth of your circuit, but it can go as low as 80% after just 10 layers, and in the worst cases, after say 20, 30, 50 layers, which are just some of the simplest quantum algorithms that you can come up with, you have a fidelity that is about 50%. Okay, for a single qubit. That is abysmal, like 3% in the case of many, many qubits. If you have, let's say, for a single qubit, a fidelity of 50%, what it means is that you have a 50% chance of finding the correct result and a 50% chance of finding the opposite result. In other words, you have nothing. Okay? So that's why it's quite important, and a way to account for all of this, a way to simulate more or less what your algorithm will be with a classical simulator before sending it to the actual quantum computer, is done by accounting for all of these kind of errors. Errors that are given to you in the calibration data in the form of T1, T2, measurement confusion matrix, reset error, and finally the gate fidelity. All of these 5 stuff are the most standard stuff that are given to you. Sometimes they give you more, but those are the most standard. Okay. What time is it? All right. I will do one more thing before letting you go, because it's quite important. It's another kind of noise that doesn't exactly correspond to any physical process, but is a good placeholder for when you have no clue what kind of error or noise is going on. Okay? It's something that is called the depolarization error. So here we had at least some understanding of what was the reason behind each and every single kind of error that you make, but sometimes you really have no clue. Sometimes you account for T1, you account for T2, you account for measurement and reset error, and yet somehow the fidelity that you observe this way is still inferior to the fidelity that you obtain in your modelization is still above the fidelity that you measure in your experiment. And you have just no clue where the error comes from. Well, in that case, you just modelize what's left of your error as with something that is called the depolarization noise. And this is the last thing that we'll do today. And it's relatively quick and easy, so it's fine. The kind of noise that it is, so it's considered as the worst kind of noise because it's the one that removes the maximum amount of information. So if you start with some rho and you apply this depolarization noise to it, depolarization noise with a certain parameter p, the depolarization noise only has a single parameter, then what you're left with is 1 minus p times rho plus p divided by the number of states, that is to say the dimension of the Hamiltonian in which rho lives, times the identity. Okay? So it means that after each depolarization process, rho becomes closer and closer to a statistical mix, a diagonal matrix with all of its diagonal entry being equal to one another. Okay? In that case, then the fidelity of let's say the depolarization process, okay, is equal to 1 minus p plus p divided by the number of states. I spare you the computation. It's relatively easy. Feel free to do it at home. Which means that if your parameter p was equal to 0 then the fidelity would be equal to 1. That is to say, there would be no depolarization. But if now your parameter P was equal to 1, then your fidelity will be equal to 1 divided by the number of states. And 1 divided by the number of states means that all bets are on, anything goes. It's the minimal kind of fidelity that you can have when you end up with a completely random state. In Qiskit, you can modelize this with something called depolarization error. Depolarization error. All right. And to account for whatever is lacking in your fidelity, after accounting for T1, T2, measurement error, and reset error, you can use, for example, the depolarization noise if you have no more calibration data. All right, and why is it a good idea? Well, it's because it's the worst kind of noise, so you are always accounting for the worst possible thing that can possibly happen. And with that, I guess I will finish today's session. There is a bit more in the notes, and they are about how in Qiskit are all of these noise implemented. So what are the operations done on specifically on the density matrices? I guess it's not that crucial, so maybe have a look, but don't sweat it too much. It's not that important. Another thing that I would have liked to see with you is what we missed last time. That is to say, the distillation and the purification. That would have fit perfectly after the depolarization noise. But so I encourage you to again look at the notes on your own. It is quite easy to figure out on your own. There is just one step of the computation that is just given to you, even if the computation is not that easy. You just accept the end result, and you will see everything is fine. You can do the computation at home if you want, but it's not as easy as understanding the process altogether. And with that, I guess I conclude here. I will take your question now, and if you don't have any, I wish you the best. Do you have some questions? I guess not.
I wanted to ask about the graded exercises. So, what exactly makes me a no-show for an exercise? Like, can I just solve like part A and B and hand it in?
Yeah. As long as you give a copy with your name and I don't know the title, you're good. That's a show.
Okay. So
Ideally, try to do a bit more.
but I
okay.
could solve no exercise and just get to.
In principle, yes, but at least give it, I don't know, half an hour.
Okay.
Okay. Otherwise, it will feel a bit. It will make us feel very sad, and you don't want us sad, right?
Thank you.
Yes.
For the projects, it's for the industry projects, I expect 10 minutes of questions plus 5 minutes of questions. I
Yes.
think that's a typo. Should be 10 minutes.
No. It's because it's not a typo. Because in industry talks, people are always very busy or very bored, one of the two, and so you really have to like excite them for a very short time to make them happy.
Okay.
So this is on purpose. In research, people are paid by the state. They have all the time in the world or something like that. So you have long questions. They really ask on every point of details. In the industry talk, you have the elevator pitch, no more than that. A big elevator, but no more than that. So it's not a typo.
Okay.
And of course, this increases if there is more people in the team.
You're the right guy. Thank you.
Give you all the opportunity to say something.
Which is bizarre because it almost never happens.
Oh, okay.
So you're one of them,
Yeah.
and you're the higher mark Oh, really?
Probably, I was like, thank God I spent so much.
Yeah,
Right.
that's you. But
Okay.
there's another 420, but that's bizarre. It almost never happens. Usually the all numbers you. It's just you two are from 2 different years, I guess. But anyway, yeah, I'll ask Zoe. I don't know really get time. So. It should be just her name, Zoe McIntyre. After reading about the series. And there's no accent or anything.
I have forgotten to send you my email address.
Ah.
I will do it tomorrow.
Well, I've put everything on GitHub now,
Ah, okay.
so you don't
No
even need it.
problem.
Because
Yeah.
I
Yeah.
think it should have been a bit more clear.
Yeah, I did not do it earlier because the GitHub account is James's GitHub, and I don't know if he wanted me to pollute his stuff with mine, but he was fine with it. So,
Okay.
so that's why it
Go in the files and
So you don't need any. There is nothing that you need to do with Adam.
But you can email her.
Adam may as well not exist. It doesn't matter. You have everything.
Okay, very good. See you. Bye
See you.
bye.
I hope you enjoy.
Will we get
Yes.
solutions
Great.
that sort of more
Yes.
The project.
Yes. Yes.
What are
If you
like?
want,
Because
because
I missed the last lecture, so I wasn't. There's the 3 grading schemes,
That's right.
which we are supposed to like choose one of them.
Yeah. You
for
choose
us.
whichever you prefer.
Okay.
One per group.
Okay. How many people do you do?
So from 1 to 3, it can be more, but there must really be a good reason.
Okay. And there's no. Do we have to get our topics approved or what?
So yes. So if you look at what is written on the GitHub,
Yeah.
you have to send us an email with your choice of the project mid December,
Okay.
and basically for the topic of your project does not we don't like it, then we will tell you no, and you'll have to find one in emergency. So the best is to talk to us about your project beforehand,
Yeah.
to have a little test, and like maybe if you have an idea you can even tell me now. I tell you, yes, it's a good direction or not, and
I mean, I was thinking of, because I saw the quantum ping pong, so I was.
quantum ping pong.
Yeah, on
Okay.
GitHub it was the link was given for it.
Okay,
So
okay,
I was
okay.
thinking something around like maybe quantum, like tic tac toe or something.
Uh-huh,
A bit.
uh-huh.
I did a bit of research for it, in which it was like it's few bits if I'm not mistaken, because it will be there will be 3 states like 0, 1, and 2. So 0 will be empty, 1 will be filled with space, and it was. Yes, I was doing some
Okay, yes.
very rough research on it, so I might be wrong on it. So I was like thinking of making a quantum ping.
So on the principle, that's just fine. Now, as it turns out, a quantum tic-tac-toe already exists.
Oh,
So maybe it would be nice if you do something that is a bit different. It can still be a tic-tac-toe, but ideally not the exact same tic-tac-toe that already exists.
I didn't even know that it
Yeah.
exists.
But that's why I'm telling you. So on the principle, that's just fine.
Yeah.
But try to do something somewhat different.
Okay.
Okay.
And can I find that one easily online so I know? Okay, I don't like
I think so.
even accidentally,
I think so. Worst come worst, when you give us, when you give your email in December, it will be with a bit of
yes,
details,
of course, with some.
and there we can see.
Okay, but otherwise the topic sounds fine.
Otherwise, the topic is fine. But so I guess you go in with the industry stuff, more or less, or I
So
guess the
it's going to
balanced
be
one.
I thought the balanced one was more.
No, balanced one
lenient.
can also work.
Yeah.
Balanced one can also work.
Because I looked at the grading schemes and the balanced one was, I think, the most forgiving
Hmm.
kind of a grading scheme. So
I
that's
think
why I was
it's
like,
actually it will be the harsher one because it's the one that you're most used to,
yeah,
and
true.
therefore
Okay.
maybe I will cut this though.